At first glance, a bubble in water seems too small and fragile to make much noise at all. Pop one in a glass and you might expect only the faintest whisper. Yet when bubbles resonate, they can produce sounds that are astonishingly loud, so loud, in fact, that the collapse of cavitating bubbles under ultrasound or in the wake of snapping shrimp can be heard kilometers away in the ocean. The mismatch is striking. How can something as tiny as a millimeter bubble or even smaller generate such disproportionate acoustic power? Doesn't it feel paradoxical that smallness can speak with such a thunderous voice? The key lies in resonance. A bubble in water behaves like a spring mass system, with the gas inside compressing and expanding in rhythm with the surrounding liquid. When sound waves strike the bubble at its natural frequency, even tiny inputs of energy are amplified enormously, causing the bubble to pulsate in sync with the wave. Because water is incompressible compared to gas, these oscillations efficiently launch sound waves into the liquid, converting local vibration into far-reaching acoustic energy. It is as if the bubble is a perfect loudspeaker, tuned to a single powerful note. Isn't it fascinating that geometry and physics conspire to make a bubble an acoustic amplifier? But resonance alone does not explain the extremes. In cavitation, when bubbles collapse, the implosion focuses energy inward, compressing gas to high temperatures and pressures before rebounding outward with a shock wave. This focused release produces brief but intense acoustic pulses. A single cavitation event can generate sound many orders of magnitude louder than its size suggests. Similarly, snapping shrimp use a collapsing claw bubble to stun prey with a shock wave and a sound as loud as a gunshot. Could it be that bubbles are nature's way of concentrating diffuse energy into explosive bursts? A lesser-known fact is that the acoustic cross-section of a resonating bubble, that is the effective area over which it interacts with sound, can be thousands of times larger than its physical size. This means a bubble a millimeter wide can scatter or emit sound as if it were meters across. The efficiency is so high that bubbles are used in sonar decoys, underwater communication, and even medical imaging, where contrast agents exploit their resonant response. Isn't it surprising that the smallest spheres in water can act like mighty beacons of sound? The paradox is that bubbles, which seem delicate and insignificant, are among the most efficient acoustic devices in nature. Out of their tiny dimensions comes sound that carries across oceans. The open question is why this efficiency is so perfect. Why the physics of water and gas align to turn fragility into amplification. Are bubbles simply exploiting resonance in its purest form, or do they hint at deeper universal principles of energy focusing? Perhaps the haunting truth is that bubbles are not small voices at all, but portals where the microscopic and the macroscopic meet in thunderous harmony. When bubbles form or oscillate in water, they generate pressure waves that propagate as sound. Classically, the amplitude of sound should scale with bubble volume, which is tiny for millimeter or micron-sized bubbles. This would predict faint and barely detectable signals. Yet experiments show bubbles producing unexpectedly loud resonances. Even small bubbles can radiate pressure waves audible across long distances. The paradox lies in the mismatch between bubble size and sound intensity. Tiny sources create disproportionately strong acoustic signatures. A 1 ooh bubble collapsing under ultrasound can produce sound detectable many meters away. It is like a whisper amplified into a shout by an invisible megaphone. The secret lies partly in resonance. A bubble oscillates at its natural frequency, defined by its size and surrounding fluid pressure. At resonance, even small energy inputs are amplified into large oscillations. These oscillations radiate strongly into the surrounding medium. Acoustic resonance acts like an amplifier, boosting sound beyond what bubble size suggests. Energy couples efficiently from internal gas dynamics to external water waves. This transforms small bubbles into powerful acoustic emitters. The paradox emerges from resonance amplification of microscopic motion. Air bubbles of tilde 3 mm radius resonate near 1 ME, producing tones easily detected underwater. It is like striking a tuning fork. The vibration seems small, yet the ringing fills the room. Bubbles are effective sound sources because of the contrast between compressible gas and nearly incompressible liquid. When the bubble expands and contracts, it drives large pressure fluctuations in water. The gas acts like a spring, while the liquid acts like a piston transmitting force outward. This mismatch enhances acoustic radiation relative to bubble size. Water transmits sound efficiently, losing little energy to absorption. Thus, bubbles act as tiny but powerful acoustic transducers. Their efficiency defies naive scaling arguments. Whale clicks are scattered by bubble clouds, which ring loudly despite containing little air. It is like pushing a small lever that moves a massive door. The mismatch magnifies the effect. When bubbles collapse, the effect is even more dramatic. Rapid compression generates localized shock waves that radiate sound efficiently. The collapse can reach supersonic velocities, focusing energy into nanosecond pulses. This concentrated release amplifies acoustic output far beyond linear resonance. Sonioluminescence and cavitation damage are side effects of such collapses. The acoustic signature becomes loud enough to carry kilometers through water. Collapse turns bubbles into explosive sound emitters. This contrasts with their delicate size. Cavitation bubbles from ship propellers produce loud noise detectable by sonar arrays. It is like a balloon popping. The energy release is sudden and disproportionately loud. A single bubble is loud, but swarms or clouds of bubbles amplify sound even more. Interactions between bubbles create collective modes of oscillation. These modes radiate at lower frequencies, which propagate farther in water. Bubble clouds can therefore act as giant acoustic antennas. Their effective size exceeds the sum of individual bubbles. Collective resonance explains why breaking waves are such loud, underwater sound sources. Noise emerges from synchronized oscillators, not just isolated ones. The paradox expands from single bubbles to ensembles. Ocean wave breaking generates bubble clouds that dominate ambient noise in the sea. It is like a choir of voices, individually small, but together they fill a cathedral. The paradox also reflects the extraordinary efficiency of acoustic coupling between bubbles and water. Nearly all energy from bubble oscillations is radiated as sound, with little loss to heat. This contrasts with many mechanical systems where friction dominates. Bubbles thus act as near-perfect sound radiators. Their coupling is enhanced by impedance matching between bubble oscillations and water's acoustic modes. This efficiency explains their disproportionate loudness. Sound propagates with surprising reach across oceans. The bubble becomes a microscopic loudspeaker. Snapping shrimp use cavitation bubbles to stun prey with acoustic pulses louder than gunshots. It is like a violin string tuned perfectly to transfer vibration into the air. Because water transmits sound more efficiently than air, bubble noise travels great distances. Underwater microphones detect bubble sounds from storms, ice cracking, or marine life far away. Bubbles act as acoustic beacons, linking tiny events with global signatures. This allows researchers to monitor climate, biology, and ocean processes remotely. The paradox is that such large-scale information emerges from minuscule oscillators. Humanity listens to bubbles to study Earth itself. Tiny resonators broadcast planetary data. Oceanographers track rainfall by detecting bubble sound spectra beneath the waves. It is like hearing a pin drop echoing across a canyon. Harnessing bubble acoustics has technological value. Medical ultrasound uses microbubbles as contrast agents because of their loud resonance. Sonar systems exploit bubble scattering to characterize underwater environments. Engineers design cavitation reactors that use bubble collapse to drive chemical reactions. Each application relies on bubbles' unexpected loudness. The paradox turns limitation into resource. The tiny becomes powerful when resonance and coupling are harnessed Science transforms paradox into utility. Ultrasound imaging injects microbubbles to amplify echo signals from blood vessels. It is like planting small mirrors that reflect enormous beams of light. The bubble sound paradox is that bubbles, which should be faint acoustic sources, become disproportionately loud. Resonance, compressibility contrasts, collapse dynamics, and collective oscillations amplify their signal. Acoustic coupling to water is so efficient that even nanoscopic oscillations propagate across kilometers. The paradox reveals how scaling laws fail when resonance dominates. It shows that size is not destiny in acoustics. The tiniest voids sing with the loudest voices. Nature uses bubbles as amplifiers of sound. Bubble collapse during cavitation generates sonar, detectable noise louder than many marine animals. It is like a single violin note carrying farther than the roar of a crowd.